Hi, so this is a kind of a first draft video. I think I might make a more polished one later, showing a little bit about cameras with bath interferometers. This is the sensor and the lens, and this is 4.2 millimeter aperture, 12 millimeter focal length lens. This is a Raspberry Pi camera. I don't know what the lens actually looks like. It may be a combination of, I hope it's a combination of a couple lenses, if it's a color camera. Otherwise, you'll get some bad color effects, but for interferometry, a simple lens will work. Um, this is a Raspberry Pi HQ cam sensor. It's 5.5 millimeters vertically from here to here, and it's 3,000 pixels from here to here. This is vertical. I don't care about horizontal because the image of the diagram is a circle, and so when it hits the edge here or hits the edge here, um, if you rotated this in 3 dimensions, 90 degrees, you'd see a circle diagram on the detector. In this configuration with this mirror, this is an f4 mirror. We're only using about a third of the sensor. You might want to get a longer focal length lens, but this is a nice 4 millimeter aperture, is nice and big. That's 4.2 from here to here. I'll show the mirror later, but it's way the hell to the left. It's 116 inches. This is a 14.5 inch diameter f4 mirror. So this point is, this beam is a 1:8 ratio. So, and this triangle here is a 1:8. Let's ignore the blue line here, ignore the purple lines here for now. I'll get into those in a minute. So if this is 4 millimeters from here to here, it's an f8 beam. 4 times 8 is 32 millimeters. So it's about 32 millimeters from here to here. It's a 4.2 millimeter aperture, so it's 33 millimeters, I guess, to here. Now this is supposed to represent the cube, and you might think, well, this is confusing. My bath has all this folding of the thing. So I just simplified. Here's how the bath really is. This red line is an f4 beam coming back from the mirror. So the laser comes off here. The red lines get converged to here. That creates like a synthetic aperture, which I'll talk about in a minute. And then the red lines come back from, bounce off the mirror. By the way, this is left, right, backwards. Here I have the mirror to the left. Here I have the mirror to the right. The red lines come back here. This is from the top of the mirror and the bottom of the mirror. They converge to a point right here. And you have this synthetic aperture about 3 millimeters in from the edge of the cube. And then we're talking about putting the camera over here. The blue lines are the reference beam, which should always be larger than the test beam, the red of the test beam. If it's not larger, then you're not going to get a very good diagram. It's going to look like crap on the edges. That's not what I want to talk about. So the top of the mirror is coming back here, converging here at this synthetic aperture, and that's what this purple is showing. For you, it's somewhere in the cube. It doesn't have to be in the cube. If you can move this lens closer to the cube, you could move it outside. This is a 13 millimeter focal length lens, diverging lens. If you had longer than 13 millimeters, then it'd be easier to get that out of the cube. We don't need to. I'm just saying, you want it as far left as possible because then the camera can be farther to the left. For every millimeter you move this lens to the left, the camera can move to 1 millimeter to the left. But we're pretty close. A lot of people don't use a 13 millimeter; they use even shorter focal length, and so it's converging somewhere in here. But that's neither here nor there. So I'm just showing the cube just kind of for reference. This is 15 millimeters, and I just eyed it. This is 3. I guess I probably did it poorly because this is 7. So this is probably more like 4, so I probably should have the cube to the left a little bit, whatever. So there is this synthetic aperture that matters here. We could bring these blue paddles all the way in, or if they're outside the cube, we could put paper on the side of the cube up to here and up to here, and the camera would still see the same diagram. But you can imagine if your eye's out here and you're looking through this little hole here, you want to move your eye as close as possible to the hole so that you can see the whole mirror. And that's where I have it positioned as far as possible. I have your camera as far as possible from the cube and still not crop the diagram. So this is weird. Normal photography, you don't have this second synthetic virtual aperture here. You can look, big time. You don't have this like virtual blockage here. Why is there an aperture? I don't know how to explain it. The laser light comes here and comes to this tiny, tiny point. Really small. All the light comes to that point from the laser. Goes off the mirror, comes back to an equally tiny point because it's the mirror is basically spherical. Even if it's parabolic, it's close enough. It's like a sphere. So it all comes to a very tiny point. And so oops, this point here. All right, so let me show you an example. If you move your camera closer, I kind of did this quick mock-up. You can see you're not going to crop the igram with your lens. And notice how the image on the camera is going to be the same size either way. It's going to be about a third of the thing, so whatever a third of 5.5 is, that's about how many millimeters it is here. And it doesn't matter if the camera's here or the camera's here, you're going to get the same size igram if it's focused properly. So let's talk about focusing. So this blue line has to do with focusing. Let me get this diagram out of here. So this blue line also goes to the bottom of the mirror. Let me just show you the whole thing. All right, so there's our bath. And I don't know if you can see it, but I can zoom in a little more. There's a little gap between the blue line and the black line, but they both go to the bottom of the mirror. So as we go further to the left, they get closer, closer together, and they both hit the bottom. We're halfway to the mirror, I think. They both hit the bottom of the mirror here. There's the mirror. I made it the correct, everything's to scale, so that's the correct curvature. So the blue line and the black line come together here. Let's speed things up and zoom out more. So the blue line and the black line both go to the bottom of the mirror. But imagine you have a little bit of turn down edge. If you have turn down edge, the light's going to go out to the mirror and bounce back a little bit low because it's turned down edge. It's tilted a little different. You get a little bit of slope error, you might call it, when you're figuring a mirror. When you're looking at a Foucault image, the shading shows slope, not height error. Whereas in an igram, you're seeing height error, which is a lot easier to understand. Anyway, so this beam here is coming back from the bottom of the mirror if we have a little bit of turn down edge. But when it hits this lens, it gets focused to the same point. That's how cameras work. They're allowed to take in more light than just a pinhole, and they focus it to the same spot. So something coming at this angle into the camera from the bottom of the mirror comes up here, and it gets focused to this pixel on the detector. That's if we have it focused. This is focus affinity. If this from here to here is 12 millimeters, but I put it 12.05 millimeters because that's how far you want it apart when you're focusing at a 116-inch mirror. Now, you can't tell in the diagram that it's 12.05 millimeters, but it is. Trust me. And it doesn't really matter that much. If you focused it for infinity, then this blue line and this black line are going to come pretty close to the same pixel, and it probably doesn't matter. And I think this may be extreme turn down edge. I don't know. I'm not sure what extreme turn down edge, what one wave of turn down edge looks like for a 14-inch mirror. I'm not sure what it looks like. But anyway, so that's why we have this lens. If you took out this lens and you put the camera sensor here, you would still get an igram, but it would look like this. The edge would be, this is for a turn down or up, I forget, mirror. And so what happens is that turn down or up edge, I guess it's turn down edge. Yeah, the turn down edge is focusing outside of the mirror. So the focused would look like this. And the black lines do curve just a little bit because it's only like 1/8 of a wave of turn down edge. But you see it showing up pretty severely when it's unfocused. So this is a sign that it's unfocused. Now, if the mirror is a perfect sphere, not a parabola, no turn down edge, then you probably don't need this lens, I believe. I think. I'm not positive. I think you wouldn't even need this lens, but I'm not an expert. But it's not a perfect mirror. It's got some parabolic curves to it. If it's a perfect parabolic mirror, you've got things not coming quite to a focus here. Some stuff's coming to a focus here and here and here. And you want this lens to focus it all to the right pixel. So that when you see something in the igram that's at the top of the igram, it's at the top of the mirror. Well, that's the bottom of the mirror, but whatever, and vice versa. So that's basically it. I was going to show you, you can do this cool thing. I don't know. So you can see that no matter where the beam hits this lens, it focuses it to the same spot on the detector. And if you want to know how I knew what the size was to focus here, I mean, you can calculate it just knowing the focal length, and that it's an f8 beam. But I drew these kind of secret red lines here. And this one also goes to the bottom of the mirror, and this one goes to the top of the mirror. And I have them cross here and hit the detector. And that's where the image is going to be. Because if this lens is focusing, by the way, in real life, this is probably a doublet lens, because a singlet lens like this, you're probably going to get some color aberrations and some spherical aberrations. So they probably have at least 2 lenses in here. But this is just like a theoretical perfect lens. A beam that goes through the center of the lens shouldn't change its angle. That's one of the things as lenses. So I did this little geometric trick to figure out how big the image would be on here. I think when I did it in the email, I just used math instead. I forget what I did. I forget how I figured it out, but that's how I did it for this drawing. So what are the takeaways here? Let's zoom out a little bit. Aperture matters, and how close your lens is to the, let me get rid of that thing. Aperture matters, so the diameter of this and how close you can get. So the bigger the better, and the closer the better, so that you can get the whole beam through that lens. Aperture matters and distance matters. Zoom amount matters. So, if you can get a longer focal length, then this can go further back. You get a bigger image. Right now, you're only using 1/3 of the sensor for an f4 lens. For an f6, f4 mirror. For your f6 mirror, it's going to be even smaller. You're going to use maybe 1/4 of this sensor. Now, 1/3 of this sensor is still 1,000 pixel. That's still a pretty good igram. By default, DFT Fringe only uses 600 pixels of the actual igram. But for your f4 14-inch mirror, 14.5-inch mirror, you're going to want that 1,000 pixels. I think 1,000 pixels is going to be enough, but you're kind of pushing it. I would get a little bit longer focal length, maybe a 20 millimeter. If you can still get a 4 millimeter aperture, a 20 millimeter lens would be nice. It's probably more expensive. I think this lens was $10, so you might have to pay like $50 for that. But I think this would work. I think this would all work. You just have to get it a little. You wouldn't want it the full 33 millimeters from this point. You'd want to get it, maybe this far from the cube. And then focus matters. That's the other takeaway. If you don't focus it properly. And did I say how to focus it? You just put some paper on the mirror. You can focus it through the cube, or you can move the cube out of the way. When I say through the cube, it's really going through the cube, off this flat, into the mirror. And you want to focus it so that you get a clear image of whatever piece of paper you put on the mirror is. Or if you can see the edges of the mirror, you want to focus it so it's in sharp focus. You can just remove this whole camera and bring it upstairs and point it at a brick house or something, and put the camera 116 inches away. I get the 116 because it's 14.5-inch diameter mirror. It's f4, so you multiply by 8 because it's double the f number. It's an f8 triangle here. So 8 times 14.5 is 116 inches. So you want to focus it for 116 inches so that the mirror gets focused nicely to 1 pixel, and slight slope errors don't get focused in the wrong part of your igram. So those are the 4 takeaways. So that's it. I hope to make a much more shorter, polished, clean version of this video.